subtopic number 8, which is our second last subtopic, diffraction by a single slit. So in this subtopic, you have to be able to define what is diffraction, explain the diffraction of a single slit with the aid of a diagram, use this formula here to solve for whatever the question asks for lah. Okay, so diffraction. Diffraction is the bending of light waves as they travel around obstacles or pass through a narrow slit. So there are a few assumptions for this diffraction. The assumption are the slit size should be small in relative to the wavelength of light, the screen should be far away, and the rays should be parallel. Okay, so the amount of bending will depend on the relative size of the wavelength of light to the size of the slit. So if the slit is much more larger than the light's wavelength, the bending will be almost unnoticeable. Tapi kalau the slit is much more smaller than the wavelength of the light, it will be noticeable lah. Dia lagi diffracted. So according to Huygens principle, each point on the wavefront at the slit act as a secondary sources and emitting new wavelets lah, macam di sini ni. Okay, so it radiates towards the screen here. So this is the magnified view of slit lah. So the wavelets from one portion of the slit will interfere with wavelets from another portion. So di sini na wavelets ni dia ada interference sudah, which then generates diffraction pattern on the screen. Okay, so each point on the wavefront is then paired with another point. Distance dia adalah a over 2 away, which is the width of the single slit ni dia bahagi dua. Okay, so for theta equal to 0 degree, the wavelets will be going straight forward and travel the same distance to the screen. So they would arrive in phase and interfere constructively, which then produces a bright central fringe in the screen lah, kalau ada screen di sini. Okay, kalau the wavelets meet on the screen at an angle of theta, the path difference between ray 1, 2, and 2, 3, and 4, and 5 and 6, this is 1, 2, 3, and 4, this is 5, 6 is width of the slit divided by 2 sine theta lah. So if this path difference is exactly half a wavelength, which corresponds to a phase difference of 180 degree, the two waves will then cancel each other and produce destructive interference. So a dark fringe is seen on the screen. So that is just basically the explanation of diffraction of a single slit lah. Okay, so what can we see from this slit here is a pattern of light and dark fringe. So the central fringe will be white and bright, and then it gets narrower as it goes further, and then it alternates between dark and bright fringe, and the intensity decreases as it goes away from the center, as we can see here, right? Okay, so this is the formula for diffraction by a single slit, where A is the width of the single slit, theta is the angle for the end dark fringe, lambda is the wavelength of the monochromatic light, and m is the order number. Okay, so this one is for the dark fringe, this one is the formula for bright fringe. Okay, so the order number starts from 1, 2, 3 lah. Okay, so that's just a diagram, you can read this through. This is the width of the central bright fringe. So it goes from the first minimum on one side to the first minimum on the other side. This is the width of the central bright lah. So this is the formula, and then it is inversely proportional to the width of the slit. The narrower the slit, the more the waves spread out lah. So the width of the central bright is directly proportional to the wavelength. Okay, so let's look at the example. So we have light of wavelength 580 nanometer. So this is lambda, this is the width of the slit, which is A, and then the observing screen is 2 meters from the slit, so this is capital D. Find the position of the first dark image. Okay. 0.003 ka 0. Aduh, wait let me. Okay, so I have to calculate. Okay, so the position of the first dark image, it's gonna be dark fringe. So the formula is y m equal to m lambda d over a. So the formula is this one. This is dark fringe kan? This is the formula. And then the value of m for first dark fringe, m is gonna be equal to 1 lah. First dark fringe. First dark fringe. M is equal to 1. Wait, let me just calculate. It should be 1. So 0. This is 580 nanometer. -9. D is 2. And then divide by the slit separation, which is okay. So yeah, okay, so for the first dark fringe, m is gonna be equal to 1. Okay, so y1, this is 1, this is 580, this is 2 divided by 0 0.0 actually this should be 0.3 millimeter. Okay, so I'm just gonna redo that later before I upload the notes. So your answer will be 3.87 times 10 negative 3 meter. Okay, so that is the position of the first dark fringe. Next, the width of the central bright fringe, that is just W to Y1. Okay, Y1, which is this one. This need to goes from the first minimum. So that is to the first minimum on the other side. That's why it's twice Y1, which is the first dark fringe. Okay, so that is just 2 times 3.87, which give you 7.74 millimeter. Okay, so that is the width of the central bright fringe. Next, the angle for the third minima. So the angle, we are gonna use a sine theta m equal to m lambda. So we are looking for the angle for the third minima. So third minima means m is gonna be equal to 3. So this is I'm just gonna rearrange that first. So we are looking for this shift sign m lambda over a. Okay, so the angle for the third minima is shift sign 3 times 580 times -9 divide by 0.3 -3 millimeter. Okay, so kamu akan dapat the angle for the third minima is, let me just calculate it first. So 580 nano divide by 0.3 -3. So you will get the angle to be equal to 0.33 degree. Okay, so that is the angle for the third minima. Okay, example 11 pula. Example 11. When a 500 nanometer. When a 500 nanometer light is illuminated onto a single slit, a diffraction maximum of width 10 centimeter is formed on a screen 2.4 meter away. So ini adalah capital D, this is W. W1 lah. Okay, so we have to calculate the width of the diffraction maximum if the wavelength is replaced by a 650 nanometer light. Okay, so we have to first, what do we have? We have to find this, which is 2 lambda 2d over a. So we have to find the slit separation dulu. So how do we find the slit separation? We are gonna use the width of the central bright fringe when the wavelength is equal to 500 nanometer. Alright, so this is just that. Okay. Wait, okay, ngam na. Astaga. So rearrange for A. It's gonna be equal to 2 lambda 1 d over W1. So this is 500 nano. This is 2.4. This is 10 centimeters. So 0.1. So the slit separation is 2.4 divided by 0.1. So it is 2.4 times 10 negative 5 meter. So that is the width of the single slit lah. Okay, so after that kita just perlu substitute into this formula here. So 650 nano, this is 2.4 divided by 2.4 times 10 negative 5. So you get the width of the central bright is, let me just calculate that quickly. 2.4 divided by that, oops, you will get 0.13 meter as the width of the diffraction maximum. Okay, so that is A. Question B, what will happen to the diffraction maximum width if the screen is moved closer to the slit? So we know that the width punya formula is 2 lambda d over A. So if the screen is moved closer, the width of the diffraction maximum would also increase. So ini adalah the explanation lah. Okay, that is all for subtopic number 8. Alright, before that, so why did I use m equal to 1 even though in the previous subtopic I said if it's first dark it's gonna be equal to 0. For this one, diffraction by single slit, there are differences in the order number lah. Okay, kalau first dark, m dia pun akan equal to 1. If first bright, m is also gonna be equal to 1. Right, that's all for subtopic number 8.